TV ads. What are we testing with variable?
Mean.
Absolutely, and what is that? What are we testing? Remember, there's only one variable, mu. So what are we testing exactly? Because you're looking at your data sheets, and how many data sets are you seeing? Look at your data. Look at your data. It looks like there's two. Doesn't it? So the trick is, if I'm asking for one mu, boom! That's how we can make it one data set. Let's look at the average difference in decibel levels between the commercials and the TV shows. Yeah? Yeah. Let's look at the average difference. In decibel levels, in dB, between the TV shows and the commercials. Stopwatches, adorable. Now here's the deal. What you could do is run a T interval on just the TV shows, and then run a T interval on the commercials, and compare the intervals, yes? And see if they overlap or not.
Was there a certain percentage difference that you're allowed?
Just statistical significance is all I'm looking for. So all I'm looking for is not touching or touching. Is that fair, Deanne? Because I don't know what that level should be based on who calls what super loud or too loud. Is that fair? But what's the problem with running two T intervals right now?
Do they overlap at some point?
Right, that's the question. If we do that, we check for overlap or not. But even before we start doing it that way, what's the problem with that? What do you do when you make two separate intervals? What happens? You lose confidence. You can no longer be at the confidence level you want to be. So, what Lauren's going to tell me correctly is bump your confidence up. If you bump up the 97.5% confidence, then you can run two intervals, and together they'd be at 95. You guys proved that on your first exam. But then I come back with, remember what happens when you increase confidence? What else increases? I'm going to build a quiz for you guys on this idea for next week. I didn't get a chance to do it last week. Remember the chance, there's two kinds of error with hypothesis tests. One is type 1. And clearly, if you raise confidence, you lower type 1 error. Because they're complementary, right? If you're at 95% confidence, you're at 5% type 1 error. And if you punch the confidence out, you obviously decrease the error of type 1. But you remember from Wednesday, it's okay, you can say no. But the very last thing we looked at on Wednesday showed that when you decrease type 1 error, you have to increase type 2 error. And for a set sample size, that's the way it is. You can increase sample size as you guys came up with, and that decreases them both. But we're at a fixed sample right now. So I don't think we want to do that. I think we want to try to treat the data set as one data set. That's the first reason. The second reason is these are paired data. These are paired. The show is paired to its commercial. Remember we talked about that before? We can't just treat every commercial the same, because that commercial was placed very carefully after the show. This is people's jobs to do this, right? So what you're looking at, I'm going to get your question in 1 second, kid, I promise. You're looking at your first, what is called a matched pair t-test. A matched pair t-test. I got 2 of these for today for us to do. One involves you guys collecting your own data, but this is the first one. It's called a matched pair because you've got a data point paired with another one, and they have to stay together. So that's why you can't just average across the way and mix everything together, because you lose that matchedness of the show and its commercial, the show and its commercial. Go, Kate, please. Oh, did I? Oh, okay, yeah, that's it. You don't want to, if you have data that's matched, you can't treat it as unmatched. Thank you very much. Fair enough? So then the question is, how do we deal with this? We'll deal with it momentarily. Let's go through our usual shebang. Okay? So we got to set up our hypotheses. H0 and H1. All right? What he said? If mu is the average difference between the commercials and the show, what's our gut feeling? It seemed like about a third of you said commercials are too loud. Maybe it was about a third, maybe close to a half. So let's test that, right? What should that be? What should mu be?
Different, right? So it does not equal.
Does not equal, I love that. Does not equal what? Let's just check for a difference. If we check for a difference, then we can go back and see if it's actually higher or lower. Because there is a chance, of course, that the show... that the shows are louder than the commercials. That's not what we think, but... So, what's it not going to equal 2?
0.
Yes! 0!
Can we say more than 0?
Well, we can say more than 0. Let's decide on that right now, shall we? We got to vote for does not equal 0, which statisticians love, because that means that it's super strong tests. We're going to have double the p-value of a one-tailed test, which means it's harder to get statistical significance because it's so tight. So, do we stick with that, or do we go with a greater than 0 to show that they're louder? What do you think? Your guys' call.
Could be greater than or equal to.
Could be greater than or equal to, although technically, because it's continuous data, we can ignore the equals, if that's okay. I mean, mathematically, it doesn't change anything because it's an infinitely skinny sliver. Kate?
I feel like the argument is that TV commercials are louder.
Louder.
Therefore, we have to.
Okay. So Lauren, with your permission, we change it to greater than. Is that okay? Yeah, I love... Now, did you catch what I said about the p-value being twice as big if we made it two-tailed? We saw this on Wednesday of last week. If you change to it... Well, you know what? Let's just do it. We'll run it one-tailed, then we'll run it two-tailed a second time, and you'll see what I'm talking about, and you'll see why, what we're seeing. So let's make it this. Boom. So the difference is positive. The difference is positive. The TV is quieter than the commercial, or the commercial is louder than the TV show. The null will be the opposite of that. I noticed on the quiz that some of you guys are writing is not greater than. I love that. I love that. I'm going to confuse the hell out of Emily when she gets back. It's great though. It's mathematically perfect. It's not greater than. I love that. It's so good. So what we're looking for, I'm going to draw a little curve if it's okay with you guys. There. There's your difference.
And 0 is really 0.
And 0, say that again, Dean.
0 is really 0.
0 is really 0. You know how every time we've run one of these tests as of last week, we put a 0 in the middle, and then I said, yeah, and contextually, what is that 0? And down below I read a percentage, or an average, exactly, Andrea. That's actually 0. 0 decibel difference. Yeah, and that's the beauty of these tests. You don't need some superfluous percentage or number. Notice how some of the stuff was pretty contrived work, like speed limits on a road. IQ. That's really contrived. It's really contrived. If you do a drug trial, you have no idea what the control group is going to come back with as a result. So very often it's more important just to see if there's a difference between the control group and the experimental group, and you can always compare it to 0 difference. So yeah, that's a huge point, and one of my favorite things about matched pairs versus the others. Mike, what's on your mind? You're thinking about something.
Everything around 0 is not going to be the same though. One standard deviation isn't still going to be 1 though. So it's just like that one.
Correct. It's still standardized. You're right. It's still standardized, and Michael's got a good point. It's still standardized in that -1 here does not correspond to 1 decibel of change. But as far as what's in the middle, 0 is 0 at this point. I love what you're saying. Very, very
It's
nice.
just unusual at 0.
Exactly. So then the question is, do we get too far away? So again, there's that line in the sand out here somewhere. There's that line in the sand, and I'm not worried about where that line is numerically. This is back to Michael's question about how many standard deviations. Because this is a t distribution, because this is t, that test statistic varies with sample size. That's why we let the machines do it for us. We let the machines do it for us and live peacefully with that. Hopefully. If you want to do it manually, by all means stick around for class and we'll show you how to do it, but I don't think it's worth it. Okay, let's identify some errors and their consequences. Yes? What would a type 1 be? Please, question first, JC, go.
Since we changed the H0 and the H1 to being louder than, should we change our definition? Because we just said that there's a difference.
Well, actually, believe it or not, the definition is fine. And this is one thing I noticed on like 2 quizzes over the weekend as I was grading them. In the definition, your claim is not in the definition. Your claim is only defining the variable. So when you put that with this, it says the average difference in decibels between TV shows and commercials is greater than 0. So that's actually okay. It's okay. Yeah, that's the whole idea is basically you take this and you bring it down here. Mathematically, actually, it should be, believe it or not, mathematically it should be less than 0. Do you see why? Mathematically, do you see why it should be less than 0? Now, I'm being a mathematical dork right now.
Because if it were greater than 0, it'd actually be quieter than 0.
Right, because of the way I wrote this, the difference between TV shows and commercials. When you think about the word difference in mathematics, it means subtract. If you subtract the TV show minus the commercial, and your claim is the commercial is louder, this should actually be negative. Don't change it. I'll change the wording of our definition.
So we ought
Does that make sense? I'll just change this.
Commercials.
Some of you don't care, and that's okay too. This is just the math guy in me going like, ugh. All of a sudden I look at that and I'm like, that doesn't make sense. Between the commercials, yes, and the TV shows. Now at the time, with a two-tailed test, it wouldn't matter. If it were two-tailed, all you're looking for is a difference. So if it punched too far out, you're like, oh, there's something going on. Then you can go back and look at it again. But now that we're one-sided, we're pointing in the right direction. Does that make sense? It's a mathematical point, but it's still a good point. Is that fair? Good. I've got questions right now. Thank you, JC, for bringing that up. I wouldn't even notice that until, well, we would have noticed it eventually. Fair enough? All right, give me a type 1 error in context. Just FYI, and this is a very minor, I'd say 1 in 30 people made the mistake. Don't just put false positive when I ask for a type 1 error in context. I mean, it is a false positive. But tell me what it would mean for this particular test.
But it's good to
If
do
you,
both, right? So
oh no, it's very great to do both. Just don't stop with false positive. I know it's a false positive. Tell me what it is for this particular test. So what would that be for this test? Good. Well, give me more than that too, because that's basically the same thing as saying false positive. Saying that the commercials are louder than the TV shows, but they're not. Yeah. Now you guys are saying the right thing. It's a false positive. Saying there's a difference when there's not. That's all great. But you see, that applies to any test anywhere. Give me for this particular test. For this particular test, it means saying that the difference is positive. Saying that commercials are louder than the shows, comma, when in fact they're not. Good! How about false negative? Be brave now. Be brave now. False negative type 2 error. Go ahead, Kate!
Finding that the commercials are not louder than the TV shows when they are.
Very good. Our drinking problem. Saying that the commercials are not louder than the TV shows, comma, when in fact they are louder. So you missed it. You missed the change. All right. Which one's worse and why? Which one's worse and why? Pick a side. Pick a side. Which one's worse and why? What do you think? Harrison's got to vote.
I think when you think they're louder, but they aren't, so there's something wrong with your hearing.
Okay, well, let's assume. I like that. I like that. But and I kind of oppose that too, being a 40-year-old geezer. But remember, these are scientific instruments measuring decibels. So it's not just one person going, "Ah, it's too loud." It's not like me, you know. It's actually a scientific measurement of loudness. But I like what you're saying. So if you trigger a false positive, it's worse, because then what might happen? If you trigger a false positive and somebody, I mean, I'm assuming a congressional subcommittee, approved this study. You get a false positive, what happens? Everybody's got to deal with that ruling now, right?
Yeah.
Everybody's going to start cracking down on, and things are going to cost more. If you're already paying for cable, it might cost more because now you got to have more regulations. That's a potential kickback from a false positive. Good, Harrison. I like that. Kate?
I would say type 2 because
Good.
in a way you're ignoring the problem.
If there is a problem, you're ignoring it. I love that. And what's the problem with ignoring the problem?
That everybody's still going to be pissed off because commercials are loud.
And maybe they even get louder, right?
Yeah.
If you miss the change, if you miss the loudness, they could just keep pushing the envelope. And this is the 6-year-old mentality I see in kindergarten
Or
quite a bit.
people could just quit having televisions with commercials.
Another kickback. It might drive people over to commercial less or commercial fewer
Yeah.
television, pay for TV. Good. Good. Please realize there cannot be a wrong answer for which one you think is worse and why. And I love the fact that we've got one person saying type 1, one person saying type 2. I expect different answers from everybody. I try to pick data sets that actually generate some kind of thing, something you would care about. So thank you guys both for that. All right. What are we up to now? Which distribution? We've already answered that. That's definitely a T distribution. Now, Kate, go.
Can I just ask a question?
Of course.
Why is it T distribution?
Why is it a T distribution? Because you're measuring an average, number one. Why can't we use a Z distribution? You might not remember the answer to this question. But, Lauren, go ahead.
C distributions gives us percentages, or T distributions gives us detail how far from zero.
Yes, if we're going with percentages, like the percentage of shows that have a commercial peak louder than their TV show themselves, then we could use a Z distribution. But as Lauren just pointed out, the average gives us more detail, not just that it's louder, but how much louder, if we want to go that route. Good. You guys got, JC, go ahead.
What about because we
We got the raw data, which we can't feed into the one prop Z test. Very, very good. I told you never to push this button. I don't want you to push it right now. But there's a t-test raw menu on your TIs. The one, that's the mathematical reason. You guys gave me the perfect statistical reason, and I like your answers better. Here's a mathematical reason in addition why you shouldn't use the Z-test. The Z-test needs you to give you the population standard deviation. Now, if I knew that, if I knew the population standard deviation, what else would I know? The population average and the population itself, and we would not be doing statistics. We'd be doing parameters, and we wouldn't be sitting here talking. The whole point of this course, you would come in on the first day of class, and I'd say, here is a decibel meter, here's a stopwatch, here's a scale, here's another kind of scale for really small things, here's a scale for really big things. I wish you well, good luck counting, go forth and count your population. That would be this class called parameters. It's freaking ridiculous. Even the Census Bureau is admitting they can't do it well anymore. The census was great when I think we had this discussion. There were 20 people and 5 horses in America. The census was awesome. How's the country doing? I don't know. George? Tom? Everybody's here. But now there's 310 million people. You have to draw samples. So that's a more descriptive answer. I like what you guys answered though, because that's the statistical answer. T is for averages, Z is for proportions, because T actually gives us a little more level of detail than Z can. Is that fair?
Yeah, I
Over
thought
answer.
maybe we went over something on Thursday.
Oh, no. Just for right now. T is for averages, Z is for proportions, and we're good to go. Fair enough? How are they the same? Oh, they're the same shape. The beauty of the T distribution, it is shaped like a bell. It's a bell curve. I mean, we use that term bell curve, and sometimes in 243 we made that a one-to-one correspondence to the Z curve. Well, the thing is, other curves are bell-shaped. I mean, actually, any curve, if you let the sample size get large enough, becomes bell-shaped. Even without the center limit theorem, which is kind of rad. We'll get more into that next week. But, fair? Okay. Now, let's crunch data. Now, I'm watching the clock. Let's do this. I'm going to run up to the office and get your guys' quizzes that I graded over the weekend. Take 5, maybe 6 or 7. Take the data, which is somewhere. Maybe it's here. Well, you got data somewhere. the decibels. Put the TV shows in L1 and put the commercials in L2. Start with that. Start with that. I'll go get your quizzes, run them back down. Take 5, take 6, take 7, and then we'll figure out how to actually turn this thing into a test statistic. Cool? Because right now it looks like we're going to have 2 data sets, L1 and L2. I don't want that. I want one data set. All right, I'll be back.